Just for 10 minutes up to the 2 o'clock break, I wanted to do a short presentation here on a topic that I know is very interesting for a lot of customers who are using RTG4 today. And this topic actually relates to reprogramming the RTG4 part in space. There's many reasons why you might want to reprogram an RTG4 in space. One obvious reason is because you have some sort of some bug or some sort of oversight in the FPGA code, and you need to change the FPGA. You don't discover the bug until after the satellite has been launched, or something like that, and you just got to reprogram the part. So that's one pretty obvious reason, but there are others. For instance, in the science community, as you build satellites with instruments with much greater resolution than any previous instrument, you may be observing a physical phenomenon, some kind of astrophysical phenomenon with greater resolution than you previously ever been able to view it. And because you haven't looked at it in that detail before, the algorithms that you use for signal processing might be kind of a best educated guess at the time that the satellite is integrated, and you might need to fine-tune those algorithms based on what you actually find when the instrument gets out there and starts observing whatever physical phenomenon it is. In the world of reconnaissance satellites, you may be facing a changing threat situation, in which case new threats may become evident after the satellite is launched, and you may need to fine-tune the signal processing algorithms to account for changes in the items of interest or in the threats. And then, of course, there's situations which we all dream of, which are the satellite gets launched, it fulfills its primary mission, the hardware is still functional, the instruments are still good, the original science mission has been accomplished, and you might as well reuse the hardware for something else. So you might want to reconfigure the hardware. So RTG4 does support integration or reprogramming after integration during spaceflight, but there are some constraints to be aware of, and those constraints are radiation related and also data retention related. So the first one's a retention issue. If you reprogram the part more than 200 times, you're going to find that the data retention starts to become compromised. In other words, that 201st time that you reprogram the part, you won't get 20-year retention. The retention will be a little bit less than that. And Min covered retention in her presentation earlier this morning. The other reasons, the other constraints are radiation related. We've found in testing that the reprogramming circuits become inoperative at somewhere greater than 50 kRad. We tested 50 kRads, they were fine, 75 kRads, they were not. So somewhere between 50 and 75 kRads, the reprogramming circuits become inoperative. And then there's also heavy ion effects. So you can get non-destructive interruptions to the programming process in the heavy ion environment in space. And the probability of that is very, very low. As JJ pointed out in his presentation earlier today, we calculate that the probability of having one of these interrupts to programming is less than 1% in geosynchronous solar main conditions. And if you are unfortunate enough to encounter a programming interruption, then you can simply attempt to program the part again, and your chance of success again is 99% or greater. So in order to accomplish reprogramming, you need to have a controller in conjunction with the target FPGA. that controller has to retrieve the reprogramming code from a memory device that's local to the FPGA. And then it has to control the upload of the new target code into the FPGA. So that usually requires a microprocessor, and the reference design that we have prepared here does in fact use a microprocessor. You've got the choice of using a standalone microprocessor, standalone radiation hard microprocessor, or of course you can use an FPGA with a soft microprocessor core programmed into the programmable gates in the FPGA. In addition to that, you need some code for the processor to execute. In the case of RTG4, we use something called DirectC. DirectC is a Microsemi product. It's an embedded set of C code that will actually command the processor to exercise the JTAG port on the target FPGA in the correct sequence in order to upload the appropriate programming file. In the diagram that you can see here, we've got a memory device. The new programming file is programming file number 1 here. It's embedded with some DirectC code. We'll talk more about DirectC in a moment. There's another FPGA here running a RISC-V processor. This FPGA could be an RTAX device, or it could be another RTG4 device. It just has to be something that has sufficient density to integrate a RISC-V processor. And then you have the target FPGA here, which is waiting to be reprogrammed. And the reprogramming operation will take place using the JTAG interface. Also note that I've put another programming file here in the memory. You may want to have multiple programming files in the memory device that's storing the programming files on the spacecraft, but it's probably a good idea to contain an original version or a gold copy, a version of the programming file that the part was originally launched with, just in case you have some unknown errors in the new programming code. So what is DirectC? So DirectC is a set of C source code files which support embedded in-system reprogramming of Microsemi FPGAs. So we have done this for multiple generations of our flash-based commercial FPGAs, such as the ProASIC 3 family, Igloo, Fusion, Smart Fusion, and then the Generation 4 products, the Smart Fusion 2 and Igloo 2 products. And this is the first time that we're able to offer this capability with a radiation-tolerant FPGA with RTG4. So each time you implement an in-system reprogramming capability for a new design, you've got to compile that DirectC code for that specific application. You also have to have something we call a DAT file or a .dat file. So this is a data file that actually contains the programming pattern for the target FPGA. So in the case of RTG4, those files are on the order of 50 megabits. So bear that in mind when you're sizing out the memory for the system. So we use the JTAG interface. So as you're probably aware, if you're an RTG4 user, you're probably aware that you want to have the system controller in the RTG4 in system controller suspend mode. So this prevents any radiation upsets in the system controller while the device is flying in space. In order to accomplish reprogramming, you need to bring the system controller out of suspend mode and enable it, and you do that by making use of the JTAG port. So since the JTAG port is active in any case, we elected to support reprogramming through the JTAG port. There is a DirectC user guide which has more details. What you're seeing here is brand new, so the user guide does need to be updated, so you won't find any reference to RTG4 in the user guide at this time, but it's high up on our priority list to get the documentation make the documentation current. So a little overview on RISC-V. This is the processor that we use inside the RTG4. It's soft core processor. So RISC-V is relatively new in the world of processors. It was initiated at the University of California in Berkeley in 2010. It's an open instruction set architecture processor, which means it's available via BSD license, which means it's essentially royalty-free. It's not an open source processor, so the RTL is not open source. What's open is the instruction set. There will be open source implementations of RTL implementing a RISC-V processor, but it's not necessarily the case that, sorry, the slide changed automatically there. It's not automatically the case that that RISC-V itself is open source. Now, the architecture is designed for simplicity. It's a reduced instruction set architecture. The base code, or the base instructions, were frozen in 2014, I believe. So that means instruction code that uses those instructions has significant longevity. You don't expect to lose the capability or the support for those instructions. And because there's plenty of opcode space left, you can be innovative and actually add to the instruction set. If there's something that your particular algorithm or your particular implementation requires, you can actually customize the instruction set for your own application. There is a RISC-V Foundation whose job it is to promote and to safeguard the RISC-V concepts and architecture. Microsemi is a member, and you can see there's a variety of other organizations and companies who are members, many of them leading companies. So I think we're in very good company here. Some across the aerospace and defense market segment as well. So the implementation of RISC-V in our reference design here is actually one that was developed onshore in the continental United States, which is another advantage of going with RISC-V. The fact is you can have onshore development of the RTL. The RTL can also be inspectable. So for those of you who are doing contracts on government systems where IP needs to be inspected and vetted, this lends itself very easily to that kind of situation. The implementation of RISC-V in the RTG4, it occupied less than 10% of the available resources of the part, so there's plenty of room left over to do other functions. And the performance in this case was about 70 megahertz. So the reference design that I've made, that I've referred to, uses two RTG4 development boards. One of the RTG4s is running the RISC-V processor with the embedded Direct-C code, and that RTG4 actually reprograms the other RTG4 using the JTAG interface. So the reference design is available from Microsemi. The email addresses on the screen there for myself and for Min. Contact us if you want to get access to that particular reference design. So that was a very short interlude. Thank you very much for your time and attention there.